Yep. Well, good afternoon, everyone. First of all, I want to thank the organizers for the invitation for to present our work, which is a fiber-optic sensor for directional bending monitoring based on a pattern recognition algorithm. This is actually like something we proposed, like a different method to do it. In fiber sensors, we have several works where you can do this bending monitoring, but the novel side of this is the implementation of pattern recognition. Okay, allow me to go straight to the introduction. So bending monitoring, we have we can see this as one direction bending here. Also, two directions. We can call it left to right. Could be in any two directions, but in the same plane. And what we call directional bending is this bending in any direction. Also, we see here a structure where we have one fixed side and then one free end side. But we can also think in some experiments where both sides are fixed and then one is movable. So the bending is when these two fixing ends approach, and we have the bending. And then most of these bending monitoring has been done with fiber interferometers, and normally these are formed with splicing two different fibers, a single mode fiber normally, with some other fiber which could be microfiber, multimode fiber, multi-core fiber, photonic crystal fiber, ring cone fiber, and hollow core fiber, etc. So many ways of doing this. Then, when we have these interferometers, we get some interference signal like this, and as we apply the bending, the spectrum will shift, will change the phase, or the amplitude will change. So that's what's normally done. Here I use some figures from some papers that are here, seated here. For instance, for that one, for one, the bending monitoring one direction, they use a multimode fiber and then a three-core fiber and a multimode fiber. So they form a Mach-Zehnder interferometer type of thing. So they measure in transmission. We can think that both sides are fixed and then they move one side. In the second example, they use a 7-core fiber. This is not my work, but yeah, when people do bending monitoring in two directions, again, what I call left to right, they use some asymmetry in the structure. It makes sense to have an asymmetry to identify which direction we are bending the fiber. So in the first example, we have here a microfiber spliced between two sections of a standard fiber. And in the second example, we have a three-core fiber. Again, there is an asymmetry in the structure, so they were able to identify which direction they are bending. So for directional bending, and this bending in different directions, there are some examples as well. In the first one, we have 4 fibers placed around this tube. And then on one side, they have the optical source, the LEDs on the side, and on the other side, they have the photodetectors. And looking at the attenuation in each and every fiber, they are able to identify the direction of the bending. In this other example, they use 3 fiber Bragg grating sensors, which are here. They are placed next to aluminum rod, very small aluminum rod. So they are able to identify the direction by monitoring the shift in the Bragg wavelength of their sensors. Well, here, what we propose is to use one fiber, one source, and one detector. We use multimode fiber. In this case, it has an elliptical core. We splice it to a standard fiber. We don't really need to mind the direction of the core. So for that, we don't, as I said, we don't mind. We can see here the intensity distribution at the output of the fiber, at the tip of the fiber. So we do have several modes traveling down the fiber. We don't really mind which modes we have. And we have this interference spectrum coming from the interference between modes. In this case, we have several minimums, several maximums, so it's different from that sinusoidal signal that we saw before, but it's exactly what we want. We also suggest to use a flexible rod, and then we bend the, well, we put the fiber around this flexible rod, and then we have some fixing points along this rod. Then we place the fiber or the flexible rod in this structure to be able to bend in different directions. So what happens is that if we do the bending in one direction in 3 different positions, we obtain a spectrum like this. Here, it's not very clear we can track a minimum or track a maximum. But what we do have is a very specific signature for each position. So, and that's what we identified, that for any direction and amplitude of bending, we will have a very specific pattern. And that's why we are using this pattern recognition algorithm. Then, in order to use this algorithm, some features needs to be extracted from this signal. And this is just an example. We need to obtain a feature vector for each position, which it's very, very simple. Some of the characteristics we obtain is, let's say, the global maximum, the global minimum, number of maximums, number of minimums, just to obtain the characteristic vector for each direction and amplitude of bending. So let me try to explain how this works. We use a very, very simple algorithm in pattern recognition because, again, this is just to keep it very, very simple. Then we have the training signals, as I showed you in the wavelength domain, where we obtain these features, these characteristics. So with this vector, we can actually train the model. And that means that we have this vector and we'll give a specific bending angle and amplitude in a specific position in this multi-space. And that will be for the rest of all the different bendings and different angles. And then we will allocate what is called a class. So each of these will be one class. And then when we have the signal that now that we are measuring, the feature vector is obtained again, and then is introduced into this model. And then it will classify, it will identify in which of these groups or classes, in which class actually fits. So the way it works is like this, very, very simple again. So I was saying, we have this will represent each, it will represent one direction and one amplitude of bending. This one will represent another, and this one another. So when we have a new measurement or an actual measurement, this one will be allocated to one of these classes. Then the way this is done in this algorithm is a very well-known thing. It compared by pairs. It takes first 2 of these and have an hyperplane between them and identify on which side actually is seated. And then the one obtained like more times after this classification with all these different vectors is the one assigned. Sorry. Then when we test this experiment we obtain like we can identify all these different directions, of course, after the algorithm was trained. So it was actually a very successful way to do this bending monitoring in many directions. What we try as well is to evaluate the precision of the system. And for that, we do the dot product between these vectors allocated in these groups, these classes. And then with the angular similarity, we kind of have an idea on how this behaves. So when we have similarity close to 1, which is here where we are seated, well, the system has high precision. So just to make a zoom on these 3, here is the way it looks like. But again, we can see that we are in very close to 1. So it was a good result. Then we can also do a modeling of this trajectory and then get the projection of the bending in the actual experiment. This is the flexible bar that we use, the flexible rod, and the fiber is it's around this piece of flexible rod. We have another experiment, and here we compare 2 fibers. As I said, the first one was the multimode elliptical-core fiber, and we also test multimode standard fiber. So the core now is the one we know, the circular one, and we tested in different experiments, but it's bending at the end of the day. And we tried with another algorithm, it's random forest, because we were testing and we found that has a little slight better performance compared to the previous algorithm. And then we see that actually the elliptical core fiber provides better results than the multimode fiber, which is something that is expected because the elliptical core will be more sensitive to any deformation, while the standard fiber is just less sensitive to this deformation. But when we change to the somewhat more advanced algorithm, like the CNN algorithm, then we can get very good results as well with the multimode fiber. So in conclusion, we propose this different approach for bending monitoring, where we just splice one fiber. We don't need to mind the direction of the core of this elliptical fiber, but we can also use the standard multimode fiber. And this way of seeing things actually can be implemented in any other fiber interferometer. We just need, as I show you, some signal that looks a little bit complicated and that is very repeatable. I mean, to use the different maximums, different minimums. Okay, and this is the people involved in this work. This is work in collaboration with CO, it's the research center in Mexico, and Université Laval in Quebec.